Hello, everyone. Now, today's topic will be about the functions and the control system toolbox. We'll have some tasks and we'll try to write the code for them. Now, let's begin actually. And our first example is about the factorial, where n factorial is equal to the multiplication from starting from 1 up to the number itself. And we also have these nice properties where 0 factorial is equal to 1, 1 factorial is equal to 1, and then we have n factorial, which can be defined of n times n minus 1 factorial. Now, this will become handy in one of these tasks below. Now, let's write the code for factorial using a for loop, which is quite simple. It is basically the following. We want to calculate the n factorial. So we start with 1 increments up to n. And our result should be result equals result times I. Now, if I define result equals 0, then obviously the multiplication will not make sense because 0 times anything is going to be 0. So we have to start the result variable equal to 1 in order to not mess up the multiplication here. So this is basically the code for factorial, and let's see if it really works. Of course, we need to look for, let's say, 5 factorial. And let's run the code and look for the result. 5 factorial is 120. So this n factorial result. There we go. Of course, instead of n, we should maybe write down the number here. And as you can see, I'm using the string constructor here, or the function called string, which takes in any argument and obviously converts it into a string, which was defined by double quotes here. So I can add double quote strings to each other. That means that it will just create a whole new string out of that. So let's say n factorial equals 120. There we go. Now let's try to write the code using a vector. Now, here by vector, of course, we mean that we already have a vector here. So let me show you that. You can see that actually the for loop in MATLAB, if we use it like this, if we use this notation here, it is actually not a for loop at all, because it uses a pre-calculated vector. And if you look close, or if I rewrite this for loop for, let's say, 5, all I'm writing down is 1, 2, 3, 4, and 5. So this is not the conventional for loop. This is actually called something else, namely the for each loop. Now this variable here is going to be equal to each of this vector, each member of this vector. Therefore, this is more of a for each loop. So you can provide a vector. You can skip maybe 4, for example, if you have reasons for it. And of course, I should maybe write it down like this. You can see you don't really have to increment by 1. You can just provide a vector, and the for loop will just use each element here 1 by 1. So if we want to use a vector, what we can do is we can actually skip the for loop. We don't really have to use the for loop here. And of course, we have a notation, but I'm going to show you this one first. And we have called something called product, or prod for abbreviation. And you can see that MATLAB has these kinds of functions. It takes the product of elements. So it seems like if we have a vector, for example, vector x, it will just go ahead and use a for loop and calculate the multiplication. But in MATLAB, when we use these types of vector operations, it's quite fast. It's faster than using a for loop. It is optimized that way. And therefore, whenever you can, you just have to use the vector operations instead of the old school C-type for loops or while loops. So MATLAB has its strength in some cases, and this is one of them. So if we take the product of the vector, and if I just place 4 back into the vector, as you can see, we have 120. And of course, I can just change it to 1 with 1 increment up to n. And if my increment is equal to 1, I don't really have to specify 1. So you can see it still works. And I can quit just creating a vector and then taking the product of that. I can just directly provide it to the prod function here. So this will basically generate the same result. So let's plug it in. There we go. Now you can see that this is kind of the old school way of doing things. You define a variable, then you have a result variable. You have a for loop start with I equals 1, increment by 1 up to n, and then multiply everything with result and store it in a result and then display it. But in MATLAB, you have some convenient functions where you can just create a vector using a notation and then use the prod function in order to get the product. There's also a sum. So you can also look for the sum from 1 up to 4. It's basically 4 times 5 divided by 2, of course, but there's also this sum here. Then we have these vector operations where I can just define 1 up to 4 and maybe take individual squares. So I have 1, 4, 9, 16. I can do it for whatever I want. I can also divide it into 2, for example, and then maybe do some crazy operations like this. Of course, don't forget that if you skip this dot operator here, it's not possible to take the square of a vector because it doesn't make sense. It is kind of a multiplication in this case. So if you try to multiply these two, you will not succeed because this is a 1 by 4 times 1 by 4 multiplication since we are using matrices. So you might take the transpose of one of them, then you can multiply them. But then this is not really the multiplication that we maybe want because this is kind of a dot product. And you can also have a cross product if you just take the transpose of the first element. If you want to multiply them element by element, you can just do this. You can just say dot multiplication or dot power, and you will get the result that you might look after. So vector operations are important. This is basically what I'm trying to tell you here. Now let's write a function for factorial. Of course, this seems to be trivial. Factorial.m. We use the keyword function, but instead of defining the function, just think of the usage of the function. So I'm going to have a result. I'm going to call the function and provide a certain value, let's say n. So this is basically also your function definition. So function this, put an end here, and you're good to go. You have just defined a function here. Of course, what we can do is we can just take this definition here. Since n is going to provide it, we can just plug it in. And there we go. So n comes right in. We have result equals 1 from I equals 1 with 1 increment up to n. We will just multiply everything with that. So the key thing here is n. It will generate the vector and we will multiply it. And I don't really have to do anything now at this point because I'm already done with this function. If you define a output variable and use that output variable, if you assign it, that's it in MATLAB. You don't really have to, or you can't even do this. You can't even return result. You just assign result, and that's basically it. So once we have that, we can just go ahead and do it again. Instead of this, now we will have factorial. Maybe I should take it into one line. There we go. And this one, of course, works. Now, these first three ones are not really that exciting. Maybe the second one could be. Now, the last one of this factorial thing is basically the following. Write a recursive function which calls itself, which is the meaning of recursive, for factorial. Now, if you want to calculate the factorial, I'm going to change directly this implementation. What I can do is I can just create a function that calls itself. Now, this would look like this, for example. So at some point, it will call factorial for some argument, and it will return something, and somehow this will be useful. Now, in the case of factorial, since we know that we can multiply stuff using a for loop, using a vector, this might not make that much sense. But for some cases, you cannot avoid using recursive functions. Therefore, this is a good demonstration. So, yeah, remember these properties here. Actually, they become useful when you think about recursive functions. Now, we basically use identities in order to create recursive functions because, for example, if you look at n factorials equals n times n minus 1 factorial, you can see that the factorial operation is kind of divided into the part where we have n, and then we have the previous number, or yeah, previous number in this case, and the factorial of that. So if we carry on doing this, what we can do is, for example, we can look at it like n factorials is n times n minus factorial. So if I have a way of creating this, since I'm going to call myself, it would look like this for this function. I would just use factorial n minus 1. But of course, we also need to use the identity here. So my result here would be n times factorial of n minus 1. Now, if you think about it, what the factorial n minus 1 function would do is basically it would call n minus 1 times the factorial of the preceding one, n minus 2. And this would go on and on like this. So it goes on and on like this. At some point, I should reach something that will return a value so I can stop this process. It's kind of a for loop, but it could be an infinite for loop. So in order to avoid infinite loops or infinite calls, I have to have a stopping condition or stopping point, sort of. So, and we have that here. We have 1 factorial is equal to 1 and 0 factorial is equal to 1. So what I can basically do is I can just say, okay, if at some point n is equal to 1, for example, then I know that the return value should be equal to 1. And that's basically it. So at some point when we call something factorial here, and if that something is going to be equal to 1, then it will return 1, and then we will have calculated the whole factorial that we are after. Of course, in this case, we're just going to take this condition, if n equals 1. If that's the case, then result is equal to 1. End of story. Of course, we have an else statement, and it would look like this. Since this is the result, I'm just going to assign it like this. So I'm checking for n equals 1. If that's the case, return 1. Otherwise, just call, for example, if we have provided n equals 5, it will call 5 times factorial of 4, then n will be 4. It's not equal to 1, so 4 times factorial of 3. 3 is not equal to 1. 3 times factorial of 2. 2 is not equal to 1, 2 times factorial 1. At that point, it will be equal to 1, it will return 1, and we will have the factorial calculated. So it is kind of a for loop if you think about the recursion, but since it calls itself over and over again, but at some point it stops like a for loop and you have the result. So yeah, there's also the case where n could be directly equal to 0. So we should maybe also take action here if it's equal to 0. So if n is equal to 1, or if it's equal to 0, the result should be 1. I'm going to play something else too. It could be the case that n is provided negative. Then I'm just going to return maybe not a number, something like that, to indicate that something went wrong. You have this so-called not a number, and it can be useful for such cases. You can even generate a not a number vector. So if something goes wrong, you have to assign it, just use none. And you also have inf. I think inf is kind of also a vector generator. So you can have infinite, which is basically 1 divided by 0 in this case, to indicate that there's infinity, there's a thing gone wrong, so have another not a number. So as far as I know, correct me if I'm wrong, the negative numbers do not have a factorial defined. So we just return none. And let's get rid of this whole thing here. And let's run our code. So you can see it still works. So let's increase maybe the number here. Let's look at 10. And what we can do is, I'm not quite sure if it's going to be a healthy calculation, but we can try to do something like this. Tick tock. This is kind of a clock sound. We have a tick and a tock. And this tick starts the timer and tock stops the timer, and the time elapsed between these two calls here will be displayed. So let me show you. So it takes 0.0012 seconds to calculate that, for example. What you do is you just start it again, stop it again. I'm not sure if this is going to be important or relevant at all. You can see, yeah, it's kind of displays some numbers, but is it really important? I'm not sure, because it's not really a big example. So let's try something like this, maybe. But yeah, we cannot really measure the time, but we can see, the only thing that we can see is, if I'm not wrong, the first one, the for loop one, is quite slow. But yeah, it's a matter of split seconds, so I'm not really sure if this comparison even makes sense. But yeah, the for loop is not really fast in MATLAB or in any other programming language. So if you can avoid it, just avoid it. Recursion could be a good thing, could be a bad thing, depends on your application. But this is the result that we end up in. So let's continue. Now, our new task is to define a transfer function, gs equals 1 divided by s plus 1, and plot its step response. Now this is also quite easy. So let me come here. This is more about the control system toolbox. So what we can do is we can just define transfer functions using TF. And TF expects us, so if you don't remember, you can just say help TF. It expects us to provide it the vector of the numerator coefficients and the vector of denominator coefficients. So in this case, since we have 1 divided by s plus 1, we will just provide 1. The numerator is just a scalar 1. But here, instead of s plus 1, we will have 1 and 1. Now, it is important to note that this is a descending order in terms of power. So we will have s to the power of 1, s to the power of 0. And these coefficients are then multiplied with the corresponding expressions, added up together until you have your polynomial. It is important because if you mess up the order, since this is s squared, s to the power of 1, and s to the power of 0, this is basically 2s squared plus s plus 1, But if you mess up the order, then you could also end up in s squared plus s plus 2. These are not the same. In control engineering, we most of the time like to have this notation, this descending order for the polynomial coefficients, because we can reconstruct it. We use it in lots of places like the root Hurwitz criterion or the root table generation. We like to use it like this. And this goes for the transfer function too. So if I want to, for example, define s squared plus 1, I'm just going to place a 0 here. This is the s squared term, s term, and then this constant term. Now the step function, there's a function called step, gs, and we can just go ahead and look at the step response directly using this function. Now, as you can see, it seems a bit ugly. And the reason for that is that we have 1 divided by s squared plus 1. We can go ahead and zoom in a little bit to see what it really looks like. So let's zoom in a little bit. You can see it's a sinusoidal wave. But let's change our system back to our original one. Just get rid of that. There we go. Now we have the step response. It looks like this. Most of the time, I don't really like to use this default step function result because, well, it is not easy to, at least for screen recording and stuff, or to prepare reports. It's not really pretty in my opinion, because the line width, the whole thing, the grid, it's not visible enough for me. So in those times, maybe I have that already. So for those times, I can just go ahead and acquire the result here, y equals y comma t equals step. And let me remind you that if you use a bracket and then multiple items in that bracket, it means that this function returns multiple results. So we can just catch them by defining a sort of a vector, because we use brackets, square brackets, to define vectors. This is kind of the same notation, so we will get the y-axis or the response itself and the time vector at once. So you can see we have a vector that shows us time, and we have the y vector here. And we can plot it ourselves, which I'm going to show when the time comes, I guess. Yeah, we are going to use it here. So if you're interested in the step response of a transfer function, you just define it using this, and then call the step function, and you are good to go. If you want to look at the unit feedback closed loop transfer function, then you can do two things, actually. Let me show you the unit feedback setup. It's basically this here. This is the unit feedback setup. It's just placed in the feedback. Here we have a negative sign. I cannot place it here, but you get the idea. Now, you should already know that we can calculate the closed loop based on this connection. We have the formula for it, which goes like gs divided by 1 plus gs. You can do it like this. You can just use the algebraic method here, or you can also use the feedback command, which expects you to plug in the feed forward path, the multiplication of all the things that are on the feed forward path, like gs in this case, and the feedback path, which is basically just 1 in our case. And it directly calculates the negative unit feedback, or negative feedback in this case. If you want to have positive feedback, you just provide an extra negative here, but we don't really have that, so we can use this. So, of course, this is not a command at all. Maybe we should also get rid of this. There we go. But you can see there's a difference. Now, using the algebraic method, using the direct calculation method, So let me just get rid of it. By using this expression directly, I get something else. But if I use the feedback command, I get this result here, which is basically not that interesting. They are the same transfer functions. And if I want to prove it to you, what I can do is I can just use the ZBK 0 pole and then some gain representation. So it will show me the zeros and poles and of course the gain. Now you can see that it is basically the same. The only difference being that we didn't cancel out s+1 with s+1. So yeah, that's kind of missing here. But the feedback function carries that out, does it for us. And there's a way of getting rid of this, which can be done via the following. We can use minreal, which stands for minimum realization. By definition, it will get rid of pole zero cancellations. The minimum realization is kind of a different definition. It is more about the controllability and observability of a system. The representation should be both observable and controllable, and the cancellations therefore should be done, which is a deeper topic for now, so we're not going to go into detail. So you get the zero pole gain model and you got rid of that unnecessary stuff. Of course, you don't really need to use ZBK at the moment. You can just plainly use that, but you have to remember that minreal has to be called. So if you think about it, it doesn't really make sense if you are using this approach, 2 lines of code, and you're calling minreal anyway. So why not just call feedback and provide the according data? So store both step responses in individual vectors by both, I guess I mean the open loop and closed loop, and plot them together or on top of each other on a plot. So of course we can do the following, by the way. Let's use this approach here. Let me get rid of this. Let's suppose we have one open loop transfer function and another one, which is a closed loop transfer function. And we want to compare the results. So I can compare the step responses by just providing multiple transfer functions to the step function. And it will do the job. Let's see. There we go. We can see both of them on a single plot. I can also kind of alter the style of the plots. For example, I can give it a black color. I can say this transfer function has this color, and let's have the closed loop in blue. So I can just change that. There we go. We have kind of changed it now. But at this point, I guess I can do the customization that I've talked about. So we can use y, t, and then step response. And we can just go ahead and plot t, y, give it a certain line width, maybe also a color like this. So you can increase kind of the visibility or the visual aspects of your step response in this case. And I can go a little bit further by, first of all, defining a figure, which is basically already figure 1 by default. And I can also enable something called hold on. And this hold on is just to not erase upon multiple plot calls, because if you don't do this, what you end up being seeing is going to be the following. So this is TS. I'm going to give it a blue color here. So if you write code like this, you expect to have 2 different plots on top of each other, but that is not how plot works. Initially, it will just get rid of the old data, wipe out everything, and then plot freshly. But if I want to prevent that, I can just say, hold on, don't clear all what you have plotted, and then this would be the result. But in that case, before I do such a thing, I should clear the figure manually. So CLF stands for that, clear figure. I'm going to call it manually. I can also place grid on in order to have a more readable plot. I have a grid behind the plots here. By the way, I can see that comparing these two for only maybe 4 or 5 seconds could be enough, but it seems like one of them is too long, one of them is too short. It kind of looks awkward. So what I can do is I can just provide the step function here a certain final time, sort of. So let's say 6 seconds, for example. I can just provide it the number 6 here. And you can see that the point where the plot stops is exactly 6 seconds. Now I can compare them. By the way, I can also customize the figure itself. I can say the label of the x-axis, just give it a name, should be equal to time. The y label, the label of the y-axis, should be yt. And then we could also assign a certain title, like step response comparison, for example. There we go. A more visual and kind of a plot that should be like this. So a more informative plot. Yeah, that was what I was looking for. But still not enough, because we don't really know what the black one stands for, the black plot, and what the blue plot stands for. So there are, again, 2 ways of doing this. You can just call the legend function, provided, for example, GS and then TS. And if you run it, it will show now the legend. And in the legend, you will see that, okay, it is the step response of GS, the black one, and the blue one is of TS. But if you, for some reason, have to change the order of plots, let's see what happens. Well, you've missed the plot. You have to go to this legend and update your legend data, which I don't really like. So instead of doing it like this, I recommend you to skip this, call legend show. And what you can do in MATLAB is you can just assign these values, this text data, to the plot itself in one line. So you can just say, okay, the display name that is going to be used in this legend can be specified. And you can just say, okay, this is TS in our case, and the display name of this is going to be GS. So there we go. Even if I change the order of plots, it doesn't really matter because the name sticks with it. So I can use it in whatever order I want, and it will still be correct. I will not miss anything. I guess there's also something called, if I'm not wrong, there's something called location, and you can choose the best location where the legend should appear, and it kind of finds its best suited location. Sometimes you have the legend somewhere, for example, here, where it is the top right corner, but you can not really see the data. So it just places it here, so you don't really overlap anything. So yeah. Now, we did kind of this here, and in Y and T we have the vectors. Of course, I use the same variable name, so you can maybe change it to YGS and YTS, whatever, and you can store them. Now, what about subplots? You can just do this. You can just use subplots for your plots if you don't want them to be on top of each other. And you can also calculate the settling time and show them on each plot. So let's do that by just going here. Since I have all this definitions in this line, or calls, I can just go ahead and create these subplots. Let's say we want them side by side, 1 row, 2 columns. And the first one of that, now I can call CLA, which is kind of the equivalent of CLF, but for axes rather than figures, because our figure will have multiple axes on it. so we can clear them individually. And then I have this whole line for my subplot instead of having it for the whole figure. Now here, the only thing that I'm going to change is this is going to be the step response of GS maybe. And then we have GS, and then comma 2, TS, and it should be TS. So I don't think that the legend here is going to be helpful at the moment. So let's do it like this. So let's see the difference. You can see we have now side-by-side plots. In this case, it shouldn't be even a different color, maybe. It can be the same color. There we go. Now, step response of GS, step response of TS. Now, what if I want to calculate the settling time of these and then show them too? So we have a function called step info, which will just gather the information of a step response that might be requested. So like this. And this info is basically a struct variable. As you can see, it is a struct with fields, and you can use the dot operator and the name of the field in order to access the field data. For example, if you want to access its settling time value, you can just use info.settling time in order to get this 3.9121 value. Or maybe for the overshoot, you will just use info.overshoot and it will give you the value of 0 for the system. So therefore, what we can do is we can just say settling time, and it will provide us the value that we ask for. Now, of course, displaying them in the console, but not on the figure is maybe not our aim. So we can just go ahead and use this data and maybe use the title for it in order to display a title that's more useful in this case. So we could just say TS and then plus, and then convert everything into string data. So this one line here will generate the title, but it will do it after calling the step info function, since it will know what the settling time of this system is at this moment. So it will just display it to us. We can just go ahead and repeat it for this one here. In this case, it is TS. You can just keep adding info here, like overshoot, rise time, whatever, but you get the idea here. So there we go. Now we can use the title in order to compare the settling times of these. Of course, we have different systems. They will have different settling times. You can see the one on the right is a little bit faster. Its settling time is lower, therefore, but this one takes more time to settle down. So, and the code for it looks like this, and I will probably use this line of code most of the time. You'll see it over and over again, so you will get used to it. So we have kind of completed this part too. So what about a more fun exercise? Let's say, let me just copy this and create another run here. Now, instead of comparing multiple plots of different systems, what if we take the first order transfer function given here and change the p-value from starting from 1 to 5 and plot the open loop and closed loop step responses for all p-values. Now we are going to change p and we will see what effect it will cause. So we still will use this. So let me just take this title here, place it here, maybe call it this time open loop. And then closed loop, since we will have two plots side by side. We don't really need the step info here. Let's get rid of that. There we go. Now, let me show you another thing. I am creating a subplot here, and then I'm creating a subplot here. But if I'm going to use it in a for loop for p equals 1 up to 5, for example, if I want to plot it in a for loop, well, then I need to do something like this. I need to put this here and then maybe put it here, clear everything. And once I have done that, I have to call subplot again without this stuff. And then a subplot here. So it will know on which plot I'm going to plot it, because we have multiple axes here. So I have to choose the axis here. And I don't really like this approach because it will just switch between figures for different scenarios that's possible. So we might want to save the axis handle using GCA, which stands for get current axis handle. And we can get the axis handle here. Whatever this is, just save it for AX2, whatever this is, save it in AX1. And in your plots, you can just provide on which AX object you want to plot it without calling subplot now. So this kind of has a nice feature here. So you can just see the association. This is associated to AX1. This one is associated to AX2. And that's basically it. Now, the last thing that we need to do is we are changing P from 1 to 5. That's no problem. And now we have to define the transfer function over and over again. So let's take this definition here, maybe both of them even, place them here. So it is going to be S plus P. So the P is the constant term here. And we will have unit feedback, look for the step response, plot it there, look for the closed loop step response, plot it here, and there we go. Maybe we should provide a constant 10 seconds. Maybe it's going to be enough, maybe not. Let's see. There we go. Now, of course, having the same color does not really make sense in this case. We cannot see which one belongs to which one. So in order to prevent that, we can just, first of all, omit this whole thing. Don't even provide a color to it. And you can see they have kind of the same colors. Or we can also have a custom coloring here. And for that, I can just go ahead and use the keyword color and then provide it a color for both plots. Obviously, it will be the same color, but then I have to define a certain color vector, which will hold the RGB information, comma separated, and between 0 and 1. So the R value or G value or B value should be between 0 and 1. So it's kind of a normalized vector, color vector. So if I want to do that, I would recommend to switch to pvec here and take this definition, place it here. And instead of having P here, I would like to have the indices defined here. So instead of having the values itself, I want to have the indices because I'm interested in the indices to generate the color myself. And by generating the color, I mean, I'm going to pass in a floating number for red, for example, but I'm going to fix the other channels like green and blue. And therefore, if I switch to the indices like this, pvec, you can see that the variable I indices, index here, will start from 1. It will increase up to a certain length, len. And my aim or my goal here is to normalize this, divide everything into len. So let's just divide everything into len. So we'll get 1 divided by len, comma, 2 divided by len, comma, etc. It will go up to 1 because len divided by len is equal to 1. So it doesn't really start at 0, but that's no problem. But depending on len, I will kind of have this increasing color data here. So it will start dark, like black, for example, and it will tend to, or its hue value will go up to full red. So you'll see what I mean by that. So if I do this, the only thing that is left now is to just take the ith element divided by the length of the vector that I'm using here will determine its kind of redness, how red it will be. And the p-value is the ith element of pvec, and there we go. So I have this transitioning from black to red, as you can see here. Now, this keeps me help track of what's really going on here. I can see, for example, the lowest value here was 1. So if it's equal to 1, we have this plot here, and its closed loop looks like this. If I increase I, you will get this, these two plots here. And if we further increase the value of P, it will drop down in gain, but it will become faster and faster, for example. The settling time here is really low. And remember that the settling time is used to kind of decide when the system stops reacting, kind of. So when does the transience of such a system stop well at the settling time? If it's wiggling in its 2% band of its final value, then we kind of decide that that system is in its steady state. So this is kind of the plot, and this is the code for it. So we create subplots, we have a certain vector, we cycle through each element, we take the P value, since we are going to define a transfer function based on that, but we keep track of the indices in order to generate a color. Of course, you can change this color by, you can experiment with it. You can just go ahead and place it onto this blue channel here in order to get a blue color transitioning. You can also do some other crazy stuff. Maybe you want to have both of them simultaneously, so you get kind of this color here. Or you might also want to reverse it. You can also do that. So the red channel will decrease, so the redness will decrease, but the blueness will increase. So that will look like this, for example. Yeah, it goes from reddish to bluish for some reason. Yeah, you can experiment with it. You don't really have to do this, but sometimes if we, for example, increase the step size here, this might help us out in determining which one is which one. And I would like to use maybe 0 here, so I can see it definitely starts from the black one, and it has a certain limit to it because it is kind of stuck to each other at this point. It doesn't surpass this one here. So yeah, this is kind of the change that I can visualize here. So it is quite important to know sometimes the customizations, the background customizations, like the title, Y label, and then use this AX1, AX2 thing here. So it kind of saves the day sometimes. So this is actually the first part of today, and you will get the code here. And since it is a bit trivial and it is more about plotting and like writing a function to remind you of some basic stuff, I wanted to cover it now. And we will transition into this week 3 here. So I'm kind of speeding up a little bit in terms of our lecture notes or laboratory notes. So yeah, it is kind of related. Now we will look at the step response, but we already did in some sense. So let's continue on from this one here. And there are multiple ways of acquiring the step response. One of them is the inverse Laplace transform. If we have a certain transfer function, we can use the inverse Laplace transform. And we can also use the step function. So I already kind of did these two, so I'm going to skip that part, but I'm going to show you how to use the inverse Laplace transform. Now, the previous part, week 2, was about the control system toolbox. And as you can see here, we will have the symbolic toolbox a little bit more. So let me just create run 3. Now, if I want to use the Laplace transform, I have to use the symbolic toolbox. So sims s GSS 1 divided by s plus 1, because that was the system that we were considering. Now, I have maybe talked about this, but let me remind you again. If I'm using the symbolic toolbox in defining a transfer function, all I do is I will just repeat or add an extra s to it in order to notify myself that this is a symbolic variable. If it's a transfer function object, it will look like this. So GSS is kind of a symbolic expression, but GS is going to be the transfer function object. And I need this because sometimes I need the symbolic version, or sometimes I'll need the transfer function object. Even sometimes I'll try to convert one to another. So yeah, separating the notation becomes useful, in my opinion. So let's use the inverse Laplace transform. For that, I'm going to also add a symbolic variable t, the time variable here. And we have a convenient function. You can see that it is in the symbolic toolbox, by the way, and it is called I Laplace. So it will take an expression. And s comma t means that I'm giving you the s domain representation converted into a time domain expression, or my time domain variable is t, my frequency domain variable is s. So that's basically it. So this is run 3. Now, if you remember the whole Laplace domain or the Laplace theory, now you would remember that if you take the inverse Laplace transform of a transfer function directly, you'll get the impulse response. So this is basically the impulse response. If we apply a certain impulse to this system, we'll get a peak at t equals 0. And then from that peak, it will decay, because if you increase t, since it has its negative part here, the whole thing will decrease, or this is 1 divided by e to the power of t. If t increases, 1 divided by the thing, the denominator will increase, so the overall fraction will decrease. So this will fade out, but at 0, if you provide t0, you will see that it starts at 1, goes down to 0. And if you want to visualize that, you can also do that. Let's open up a figure, clear the figure, hold on, and grid on. So I want to kind of plot t comma y, and maybe black, and then also maybe a line width of 2, and that's going to be it. How can I do this using this inverse Laplace transform? Since we are in the symbolic toolbox, we can use this substitution function subs. So we can say I will have YSS, I will substitute t as a certain vector here. So let's define tvec starting from 0 up to maybe 5. And we will substitute that. So this will give us yvec and plot tvec comma yvec. Before I plot it, I'm going to show you something. So yeah. So we know what YSS looks like. We look at yvec. And interestingly, even though we have substituted in, we can see that it is kind of still symbolic. You can see x minus 1 divided by 10 minus 1 divided by 5. If you were in MATLAB, you wouldn't even see what e to the power of what it is. You would see just directly a double vector, so the values. So this tells me to convert it into a double vector here. So I'm using the symbolic toolbox, but at some point I have to convert it into a double in order to be able to call this plot function here. So you will see the difference now. Yvec, and there we go. You have your usual numerical data, and now we can go ahead and plot it. There we go. At t0, it's 1, it decays, and it takes approximately 5 seconds. As far as I remember, you can also convert stuff into string directly from your symbolic toolbox or your symbolic expression. So what you can do is you can just give it a title and directly call the string conversion here of YSS in order to show it on the title. as you can see, e to the power of minus t looks like this. Now, this is the impulse response. Of course, I'm not really interested in the impulse response. I want to have the step response. Now, if I'm going to look for the step response, then I need to remember that step in the Laplace domain looks like 1 divided by s because it's a constant and it's a unit constant, so it's 1. So its representation in the Laplace domain will be 1 divided by s. And ys in that case would be gss times us. Since this is 1 divided by s, I can just directly take the inverse Laplace transform gss divided by s. If I divide by s, then I will get the step response. And you can also see somehow that dividing by s or multiplying with 1 divided by s is kind of familiar. If we multiply with s in the s domain, we kind of take the derivative. If I divide into s, we take the integral. So the integral of impulse is step. So it kind of makes sense that we have to divide by s in order to take the integral. And since we are dealing with linear time invariant transfer functions, it kind of makes sense that taking the integral of the input results in an output which has also taken the integral of the previous input. So if we apply impulse to a system, we get the impulse response. But if we add an integrator, then we will apply step to it and we will see the step response. And yeah, this should be it, I guess. And you can also see, and it's neat, that its mathematical representation is also available at this point, 1 minus e to the power of minus t. And you can see it starts from 0 up to 1. It goes up to 1. Now, this is one way of doing it. And if we, for example, change the position of the pole, we can see how it affects it. It becomes 1 divided by 2, or a half, minus e to the power of minus 2t divided by 2. So you can see that this is basically the response, and it became faster. It sped up a little bit because we moved the pole a little bit. So yeah, we can use the step function, customize it. I kind of covered that part, so we can see. And here in my PDF, you can look it up. You can see that there's also a step-by-step explanation of the inverse Laplace transform. Of course, we use MATLAB's symbolic toolbox, but you can do it by using a pen and paper. And you have all the code here necessary for it, and then also the response here. So our next task will be about the following. Let's plot the step response of GS by changing a P as shown here on the same plot. And let's also plot the pole zero map on another plot, pair the coloring so every P value has the same color on step response and pole zero map. So it kind of is a visualization of the system and how it will respond, or what the effect of changing the P values or the poles of a first order system will end up being in the step response. So let's see how it really is going to happen. So I kind of have already the template for it. I have two figures. One of them is step response. That can be it, but let's change the other one to a pole zero map, or even a pole spread, maybe. And if I'm looking at poles, I of course look at the S domain, because of course it will be on the S domain. Now our PVAC values were 1, 2, and 4. We still have the coloring. We get P, we get the color, we define the transfer function, whereas we have P divided by S plus P. We are not interested in that. We can just call this. And there we go. Now we have a function called PZMap, where you can provide it the transfer function. And if you call it on your own, like the step function, it will just create you the visuals. You will see the pole zero map. It will generate a figure. But as usual, I'm not really satisfied with that. I want to create my custom plot here. So I'm going to call it like poles equals PZ map. So I get the poles. I don't really have to do this. There's another way of doing it. And that one is basically the following. You can just look for the denominator and get the denominator coefficients. And you can use roots, which takes coefficients and calculates the roots for it. So this could be another way of calculating the poles of the system, because all you need is the denominator of the transfer function. In this case, the coefficients of that, and the roots function accepts both the coefficients as the coefficient vector as an input, or you can also use solve in the symbolic toolbox in order to solve it. So there are many ways of doing this, but you can see that PZMap is kind of better because you can also get, since it is called pole zero map, you can get the zeros and poles, but since our system doesn't have really zeros, I'm not going to use it like this. So again, PZMap is a multi-output function. It has multiple returns here, but we can choose from which we want to. So yeah, I have now the poles, but let me remind you that the real axis is kind of the real part, and we have the j omega axis, which obviously is the imaginary part. So this is the imaginary part, or j omega. So in the S domain, this is kind of our plot, and we therefore need to use the plot function here, but the x-axis here is going to be the real value, and the y-axis is going to be the imaginary value. Therefore, I can use the real function here and pass poles to it in order to acquire the real parts of the poles. And I can repeat it for the imaginary part by providing imaginary of poles. And I'm going to just place some X's instead of poles, some crosses, in order to identify the poles here. Of course, this plot belongs to subplot 1, 2, 2. This one here, because the real part, imaginary part, you can just see it. So I'm going to provide AX2, so it will appear on the second plot. Yeah, instead of directly using KX, K stands for black and X is the marker, you can also say marker is X, because you can have a square, as far as I know, a circle or a circle. So there are multiple markers, but we can just provide it as a third option or argument. But let's provide the color that we have calculated in here in line 11. So yeah, I guess we should be good to go. Now let me recap. We have two subplots. One of them is for time, and one of them has x-axis time, y-axis y, so it's the step response. The other one is real imaginary part, so basically the S domain for the pole spread. We have a vector of poles, and we pick each pole, and we pick the index of that. Maybe it's the first one, the second one, whatever it is, convert it into color data, define the transfer function, look for the step response, plot it. Look for the pole zero map. Only poles are necessary because this transfer function has a numerator that is not a polynomial, but a constant, and plot the real imaginary parts on their axes in order to generate the pole zero map. So let's run this. And there we go. Now, I'm not sure if it's obvious enough, but one pole is at -1, the other one is at -2, and then the next one is at -4. Did we provide line width? Let me see, we didn't. So let's maybe provide that in order to increase the visibility here. There we go. I hope that it helped a little bit, at least. So yeah, having just few values maybe doesn't cut it. So what we can do is we can now increase the vector here in order to see what's really going on in this case. From 1 to 4 with 0.1 steps maybe. So we have a nice transitioning here, and we can see the effect. Maybe 5 seconds of simulation time is more than enough for this system to have a more zoomed in plot. There we go. Now we can see that the pole starts at -1, moves towards the left to -4. So it gets kind of away from the j omega axis or the origin. And since the dark color is closer to j omega axis, I can see that this dark color is a slow step response. And as the pole moves to the left on the S domain, I can see that it becomes faster and faster. And I conclude that it is faster because it settles down earlier. So the fastness or the speed of a system is about its settling down. So I can see that it settles earlier and earlier, which means that it is a faster system. Now we can also display the circles that are corresponding to the natural frequency, but that's not really the aim of today, so I'm going to skip that. But let me just maybe show you and don't talk about it too much. So we have something called S-grid, which is basically a grid. So I'm going to get rid of this grid on. This is just the Cartesian grid. This will be the S-domain grid, which is going to be a polar coordinate grid. And all you do is you provided some zeta value. If you don't know what it is, it's fine. And some omega n values. So maybe the pvec here, maybe minus pvec even. Oh no, pvec. And I say that this belongs to AX2. So let's see the difference. So you can see it has kind of these orbits now, and these orbits kind of have special meaning, but it's basically the lines where the absolute value from the origin or the distance from the origin is constant. So if you have a constant distance from a certain point, you will get a circle. Therefore, we get circles. But yeah, this is the S grid, the maybe the absolute value grid. You can also think about that. And we have also the angle grid, which is not shown at this moment. So maybe something like this would help in order to visualize that. Let's see. Do we get a line? I'm afraid not. Oh, it's of course not. Let's have 0.9. Yeah, we get this line, but it's still not that visible. Maybe increase it a little bit. So on the polar coordinates, we have the angle fixed lines, which are corresponding to zeta, and then the absolute value fixed or the radius fixed lines, which are basically circles. They are just basically complex numbers in polar coordinates. So therefore, that's basically the information that you can get. Now, you can see that customization sometimes helps you out in understanding systems or things in control system theory a little bit better. Now you can see that we also have the code here. I did use some different colors in this case. And yeah, and since I've talked about the zeta and omega n values, we also have a second order system. And I guess this will also be the last task here. Let me quickly check here. Yeah, it's going to be it. So let's talk about that. Let's create the plot that is requested here. So I'm going to also take this, call it run 5.m, paste it here, and see what it asks from us. So first of all, we are not dealing with a first order transfer function anymore. Now we have a second order transfer function. And here we will plot the step responses and pole zero maps for omega n and zeta. Sometimes omega n is constant, zeta is a vector. Sometimes zeta is constant, omega n is a vector. For most of the time, this is basically the case here. Yeah, so we can write functions and complicate it a little bit more. It would be easy, but I'm just focusing on the basics here, on the topic itself, so I'm not going to do that. But you can go ahead and write a function that does this job for you, and you just provide the arguments, and it will just generate you the plot. Now, Let's start with the first one here, where omega n is fixed and we have zeta as a value. So let's define omega n equals 1 and zeta vec starts from 0 with certain increments up to 1.2. So this structure basically doesn't change, but instead of p vec, now we will have zeta vec. It's also kind of the same. I'm going to have zeta from zeta vec, and of course, again, zeta vec. Now, when I define my transfer function, it looks like this. Omega n squared, 1, 2 times zeta times omega n, and then omega n squared. Since omega n is fixed and zeta is picked at each cycle, we are good to go. Now, I don't know what this should be equal to, but it should be enough. We are getting the step response. We are getting the poles and zeros. We still don't have zeros. We don't have to think about that. Now, what I can do is I can just provide it omega n and some zeta vec, because these are exactly the same data, and we'll see why. Run 5. It needs a little bit more. So let's increase the final time to 15 seconds, maybe. There we go. Makes more sense. Now, this plot actually defines the types of second order transfer functions in terms of its poles or in terms of its step response. When you look at a step response, you can immediately recognize the type of system you're dealing with. For example, if you look at this dark sinusoidal wave, you can immediately see that the zeta value here is equal to 0 because it's the first one in the loop. In our for loop, we start with zeta vec the 0, so it is going to be 0. And we have omega n fixed, and I've talked about the radius being fixed, since omega n is the radius, so omega n is fixed equal 1, we are on a unit circle. But we have zeta, which is basically about the angle, and we have 90 degrees of angle for our poles in the polar coordinates, and we get this perfect sine wave. Now, in terms of stability of a system, this system is not stable at all because it doesn't settle down, first of all. So this is kind of a pendulum which doesn't have friction or any air resistance or anything else, and it is just swinging and swinging and swinging forever, basically. So this is kind of that. If we add a little bit friction, which would be zeta equals 0.2 here, then the system's oscillations or the swinging has some friction in it. It loses its kind of energy. So eventually it'll settle down. Maybe it will take too long, but it will settle down. So these two poles here are on a unit circle, have a certain degree, which we can calculate, but it's not really that important at the moment. And yeah, 0.2 zeta value means a little bit friction. And since it's stable, it will settle down, but it takes too long and it has oscillations. If we increase zeta a little bit more, like 0.4, we see that it takes more effect. The friction or resistance, whatever, takes more effect, more and more. And at some point, it doesn't even swing too much anymore. It just, if the pendulum equilibrium point is this middle here, it starts from the right, we leave it from there, and it kind of stops here. So there's really hard resistance or friction on the system, which would correspond to 0.8 or even 1 at this point. These two have very high friction. And after that, we see that one pole goes to the right, one pole goes to the left. This is the last one here. And it takes even more time to go down. Now, think about this pendulum here. It starts from here, and it slows down during its travel to the equilibrium point. So all these friction types here define actually types of systems. This one here is a non-damped, a zero-damped, perfect oscillator, or a system that has poles on the j omega axis. This is not damped at all. And then between 0 and 1, the zeta value is between 0 and 1. So these four values here, 0.2, 0.4, 0.6, and 0.8, are called underdamped systems. They have damping, but they're not quite enough. And zeta equals 1, this exact point is called critically damped. It is just perfectly damped in that case, because it just goes and stops. So it starts from here, goes down and stops. This is critically damped. And if you pass through zeta equals 1, if it's greater than 1, then we have overdamped systems where the damping is a bit too much at this point. But we can decide on its behavior because we know lots of things about second order systems, of systems where we define a system in terms of zeta and omega n. And we can, for example, based on the value of zeta or the angle in the polar coordinates, we can just conclude if there will be oscillation, how much the oscillation will be, or if there will be overshoot in terms of this value, if it's going to be reaching a higher value than that, or if it's not, we can just look at the zeta value. The omega n value is just going to change the frequency. It's called the natural frequency. If you increase it like, let's say 10, we will see immediately the effect here. It speeds up, but everything still happens. And exactly as it happens, let me zoom in a little bit, hopefully. There we go. It's still the same shape, but it's just faster. So that, therefore, we call it omega n, the natural frequency. Frequency is about speed, but zeta is about the type of system. Now, we have seen the effect of zeta. Let's see what happens if we have a certain zeta value, but we are on we change the frequency. So let's see what really happens then. So let's copy run 5, run 6, and there we go. Now omega n vec will be our vector, and zeta will be, for example, equal to 1, and the values start from 1 to 4. Okay, from 1 up to 4. There we go. Now nothing will change, but we are cycling through omega n vec. Therefore omega n vec, therefore omega n, the length of omega n vec. And at this point, we're basically done. Here we will have omega n vec and zeta. There we go. So this should be actually it, I guess. So there we go. Now, yeah, okay. It seems like we messed up in the pole spread, but if you look at the y-axis maximum value, you can see that it is 10 to the power of something really low. So it's basically 0, but for critically damped systems, numerical errors may occur. Therefore, let me show you the poles. So let's display the poles. -4, -3.8. You can see the poles are there, but we have a 0i part, which is really, really low, but it is due to the calculation of the roots of these polynomials. So therefore, on the plot, it looks like we have messed up stuff, but we can fix it by just providing a y limit by zooming out, basically, for ax2. And the y limit should be between -1 and 1, so we can see the entire plot, but zoomed out, and you can see they are in fact on the x-axis or on the real axis, but it seems like they are not. So therefore we fixed that by just zooming out, because we were zoomed in and we had some precision errors there. So we can see that zeta equals 1 is critically damped, and at each time we just don't have any overshoot, and it takes the minimum amount of time to reach the settled value or the steady state value here. And if the pole tends to the left, if it's just going far to the left, it becomes faster, which was the case for first order systems. It still holds for zeta equals 1 second order systems. If we change the zeta value to a different value, like square root of 2 divided by 2, let's see what happens. There we go. We have this plot now. Of course, we are not able to see the whole picture here. If I zoom out a little bit, we see that the poles are again on their orbits, on their fixed omega n values, but we are changing the omega n value, but we are on the same line, on the same zeta line. So they all have the same angle associated to them in the polar coordinates, but their magnitude or their radius from the origin changes basically. And if that increases, we're tending to the left, the real value tends to the left. It means that still increasing the frequency increases the speed of the response, which should make sense. But there's also a neat property that we can observe from this set plot here, is that the peak values are aligned. So I messed up. The peak values are aligned. They are on the same line, as you can see here. They are on the same line. So this means that the peak value does not change. So if you are on a zeta line, then you will have the same amount of oscillation or the same amount of overshoot. So we can basically decide on the overshoot of a system and then change its natural frequency, alter it a little bit so that we get a certain settling time value or certain speed. So we can just tune the system by fixing zeta if we want to have a certain overshoot, but we can tune the omega n value in order to get a certain response for a certain speed. Now, what is the next value? 0.2. Let's try that too. 0.2. Again, we have the peak values aligned. You can see the peak values. I need to increase the time vector precision a little bit more, but yeah, it doesn't make that big of a difference. But we can see the omega n decides on its shape. But again, here, if I zoom out, we're on a certain zeta line, and the radius from the origin is increased. The system speeds up, but the oscillations are also increased. So yeah, this is the system's behavior that we get. So in the control system design course, and in this course, you have to basically associate the zeta and omega n values to system behavior. Here, we try to make this connection because in the further lessons or in the control system design course, we will use these zeta and omega n values as roots of polynomials. And in terms of polynomials, we will try to manipulate the system so that we end up in this specific zeta omega n pair, because it has a special meaning in terms of behavior. We think of a certain settling time overshoot value if we talk about zeta and omega n. We will calculate that, try to force the system to behave like the response that we have chosen, for example, from this variety of responses. For example, we've chosen the brightest blue one here. We want our system to act like that, so we need to pick this zeta specifically and this omega n specifically in order to get that response. Yeah, let's see. That's basically, I guess, it for this week. We have a different coloring scheme here, but it is basically the same. Instead of having it side by side, I have it stacked it a bit differently. You can see here that a certain color corresponds to a certain omega n value, but we've talked about this. So all the results are also available here. We have the zeta line. There's also the negative zeta line, by the way. And here, again, the same result and same result. So again, if we talk about second-order systems, because these are the most basic systems that we can work with, we have the first-order systems and second-order systems. So these are very basic systems. We should know them well. And yeah, in our case, associating omega n, the natural frequency, and the damping ratio to this system and thinking about their step response is important. It will become relevant in the control system design course. So yeah, that's basically it for this week.